Hello everyone, welcome to High Performance Computing, Advanced Scientific Computing. This is practical lecture 4.2. We will have a practical introduction to OpenFoam. So this is the part of the course lecture Advanced MPI Techniques. In the beginning, let's have a review of the practical lecture 4.1, MPI communications and data structure. Of course, the recording of the lecture is available, and you can have a detail and a review of the lecture. On that lecture, it was discussion about blocking with non-blocking communication, and there was example of the non-blocking communication with ISIL and IRC. Then there was example of non-standard MPI communication. In the second part, there was talk about the hierarchical data format, which is a set of file formats designed to store and organize large amount of data. There are two generations of the HDF, HDF4 and HDF5. HDF4 is the older version of the format, and HDF5 is the format designed to handle some of the limitation of the HDF4 library. And also APS5 simplifies the file structure to include only two major types of the object, dataset and groups. In the lecture, you can see the details, and because lecture 4.2 is a practical lecture and it could be take a longer time, so we are not going to detail of this review, and of course you can see the recorded lecture 4.1. Let's start the lecture 4.2. We will have a practical introduction on the OpenFoam software, which is open source, and we'll have a short talk about the computation fluid dynamic and why we need the high performance computing. Then we will see the structure of the code, how we can set up the geometry, meshing, and boundary conditions, how the solver is working, and it's working for the laminar turbulent flow. Then we will have an example of the fluid dynamics on the OpenFlow, and we will see how we can run the solution of the problem with the parallel computing and run it on the HPC cluster. In the beginning, I should remind you that this year the HPC course is specialized for the computation flight dynamics, CFD. Currently, the CFD one of the major area that we can use the high-performance computing, and it's a requirement because in the most flight dynamic problem, the computing is large, and we need to have access to HPC to be able to solve the problem. Basically, in the computation flight dynamics, the domain of the problem divided, or we call it discretization, in a very small areas. We call them elements or mesh, and also we have nodes. Then we calculate the solution for the problem for each node or mesh. Then we collect the data and we update it for whole domain of the problem. There are different methods: finite difference, finite volume, finite element. In lecture 8, we will be talking details about the computation flight dynamics and its different approaches. And in this lecture, we only have introduction to see how we will use it in the OpenFOAM software. Basically, in the CFD or the fluid dynamics, why we are using the computational approach, we have these three perspective and technique on the fluid dynamics, the experimental one, the analytical one, and then the numerical one. In the experimental one, it's possible for a specific problem. It's limited, there is a limitation for the measurement, and it's costly about the tools. We need a specific tool for the measurement and about the scale. For some problems, the scale is too large, and make it experiment, it's very difficult. You imagine what the instrument when we simulate the environment for a large aircraft or car. However, we are using some concept like uh, Reynolds number to make a scaling, uh, but it's not possible for every problem. For example, when you have problem with high temperature, it's very difficult to make experiment and measure it. Then the experiment is limited for a specific area of the fluid dynamic area. Then about the analytical one, it's limited and simply for the simplified problem, mostly the linear problem. Also, the analytical one, high computational cost, and we don't have an analytical solution for many problems. We can say most of the problem without analytical solution. But it presents a general solution equation. The analytical one also limited. About the numerical one, there is no limitation in solving problem if we apply sufficient method. It reduces the computational and operational cost. We can apply it for complex problems, especially when we have geometry, complex geometry. We can validate it before the application. In the numerical solution, it's essential to have the boundary condition and initial condition. And about the computing time, it depends on the computer power. This last item is very important in the HPC and why we need the HPC. When we're solving the problem in the computational approach on the numerical scale, because we have many meshes or many nodes, especially when it's 3D or turbulence node, the computing it will be so large. We have massive computing. So it's solving this problem is dependent on the computer power. Here is the point that we need the high performance computing. In many cases, uh, currently, when we are using computational programming, we need to have access for HPC. About the CFD application, it's very broad area. Here there are some examples. You can see the simulation for draining geothermal well and how it's simulating for the high temperature. Also at the COVID-19 virus time, it was many simulation there were many simulations used to study the virus how spreading in the environment. In the energy sector also, for example, about the wind turbine, there are some unknown concept. It's required to simulate the turbine of the actual size, which is so large computing. Then it's necessary to have access to high-performance computing to make the simulation. About the aircraft, this is one of the old applications of the CFD. This is on the aircraft design to study the, for example, the drag lift, the drag force, the lift force, some coefficient on the aircraft. For example, at this time, one of the open research area is reducing the drag force on the aircraft, which is required to make simulation with CFD. The other example here is the from medical study, how using the CFD for simulating the teaching of the body. The other example is application of the CFD on the car design, which is mostly used to study the aerodynamic of the car and how to reduce the force and find the optimal shape of the car. The another example, which is from recent year, is a SpaceX Dragon, which used the CFD. So we can see it's very broad area, but that's why it's very important to know about the CFD and why we need the HPC in these application. There are some codes which make possible to run the CFD simulation. There are two main categories, commercial codes and open source. The commercial codes like ancestral applied computation flight dynamic audio plugin. And also we have the open source code, which is open for one of them. We will talk about it in this lecture. Calculus has its code written by assistant professor at the University of Iceland, Pedro Castro, and quality leader, Dolphin, Lloyd, Sim, and others. One of the important things about the CFP code, the software includes the solver, grid generation, and visualization to be able to solve the problem uh, in all sections. In this study, we see a screenshot of the ELIA HPC system at the University of Iceland, and you can see about the modules that are available in the system. Here is the OpenFoam, so we have it on the system and we can use it. As an example, to show the importance of the CFD and high performance computing, in the fluid dynamic area, there is a concept is called turbulence flow. It's one of the unsolved problems. In 1941, there was theory from Tomorrow that it was imagination that could be called all the scale and size of the turbulence flow. But shortly after that, they recognized that this theory only could be called some mean field of the uh, flow and not all of the scale of the turbulence flow. Indeed, in Richard Feynman, the scientist using at the same century is mentioned that the turbulence is the most important other problem of the classical physics. Currently, to deal with the turbulence flow, the problem, the idea is using the theory, experiment, and the simulation. The simulation is part of the CFD. Indeed, we are using the CFD to make the simulation. For turbulence flow, there are three main approaches with different detailed techniques. One of them is called RANS, Reynolds Average Variance Works, which usually provide the average solution. The next one, large eddy simulation, which is with some fluctuation of the scale to solve the problem. However, it's the accuracy of the LES much better than the RANS, but it's not exact solution. But LES is much expensive in the computing than RANS. And the another one is the direct numerical simulation, which called DNS, and it's providing the exact solution, but it's so expensive and costly, and usually for the real problem and the same problem, they don't use it because it's costly in the computer. Based on these computing cost difference, uh, runs one of the approaches we mostly use in the industry for problem with turbulence flow. Then we can see because of the computing, it is essential to have access to high-performance computing to deal with the problem with turbulence. And in the fluid dynamic area, most of the flow turbulence. So we can say most of the problem we are using the CFD, we deal with turbulence flow and we need the high-performance computing. This is some example of a complex problem in the CFD, which it's required the HPC to solve it. You can see, for example, here in this figure, this is the example of the solar flare, and you can see how size of this scale, which is we call it coherent or eddy, and we use the side of the air. So we are dealing with very large phenomena, and we use the CFD, this is the simulation for aircraft, for example. And you can see how it's complex and many different sides of the scale of the flow we need to study. So we can say HPC is one of the requirements in the CFD study. Now let's continue to talk about the OpenFoam, which is an open source software for the CFD problem. It's able to use for the laminar turbulent flow and compressible and incompressible flow, and can be run on the parallel computer. Uh, OpenFOAM language is based on the C++ toolbox, and we can develop and customize it. It has a pre and post processing utilities, and it's solving continuum mechanics problem like computations like that. It's also possible to use in many areas, industries, like automotive, manufacturing, process engineering, environmental engineering. In this slide also you can see a screenshot of this decomposition of the mesh, capability of the OpenFOAM. This is one of the concepts we will talk about in this course, in this lecture, because we want to use these commands and this dictionary to convert them into number of the subdomains. For example, here we see the subdomain number 4, and there are different methods, simple, hierarchical, and there are other methods, and we will see the difference how we can make these decomposition. The software has a structure based on the two main directories, which is OpenFOAM library, and also there are third-party separate third-party libraries. For example, here we see this is the view of the ParaView, which is a software used for visualization of the OpenFOAM problems. Regarding the library and directories, the directories on the OpenFOAM related to the setup of the problem. For example, the library of the system has a control directories. The scheme solution, or also we have the constant one. We have the zero, which mostly used to set up the initial condition of the problem. It is possible to have additional directories depending on the problem. And it's the open source code, and we can modify it based on the problem. There are some cases as an example on the software, and we can use them and develop and modify them for our problem. For the visualization, ParaView, it's the most software used. It's open source. It could be modified, compiled, and customized. Currently, also many of the Python users also using ParaView for the visualization, which is a good software and software to make good visualization of the problem and the solution. It's working with all the operational systems, and it's possible to make a setup to run it on the HPC cluster with some setup on the server. Now let's have a look on the OpenFOAM environment and how it looks like. Firstly, I want to go to one of the good access for the information for the OpenFOAM. It's CFD Direct. On this website, you can see good information about the OpenFOAM. There is a user guide here with different versions, and it's helping for the user to learn how use the OpenFOAM. For example, one thing that we have in this lecture, we will talk about the parallel computing. And here you can see the difference between the different methods and how we can use it to run our problem. For example, there are different methods here. The simple one, the hierarchical one, and there is a sports one, and TTS one, and also the manual one, and you can see how they are working between. Also about the command we can use on the other computing and how we compose the domain of the problem, and how we can use the API line to run it. And we will see example of it, how we can run these kind of problem. So the OpenFoam direct, it's has a good information about this software and example. And you can see some example here about the meshing, about the foundation here, or also about the turbulence model, for example, what kind of a turbulence, as I said, we have for laminar and for the turbulence one, we can use the RAS, which is for neighbors aerodynamics, so RAS, and NES also for the large simulation, which is a good capability that we can solve different type of problems. So this is the environment about the structure of uh, the structure of the open form also. You can see here for every case we have this structure. When we have the case, we have uh, three main directory, system, and constant, and time directory, which is usually zero. And here in the system, we have this contract grid, the free scheme, every solution. In the constant one also we have different parts. So we are doing the setup here and we can run the problem. We will look on these directories on the software. Let's move to the software and see how to. Here we are opening the software here. If we go here to review, after the material support, we have it. Here we have three cases, which they are same cases but different decomposition method. Let's go to the simple one. You can see here the different directory. For example, with 0 1. This example is for multi-stage flow. So we have two different flows, air and water. And here, so we can do the setup for these, for example, CD, water. Sorry. Here we can see the information about this water, for example, about this water, the dimension, and what about the value we are using here. The value is 300, about the temperature. So about this dimension here, it's important to uh, be familiar with the equation in the fluid dynamic area, and you can understand this term and this coefficient, and how we can do the setup. Since we are not going to keep the fluid dynamic here, just we will look at this structure of this code and how it works. So here we can do the setup. Usually when it's zero, that means it's the initial condition. So we can look on the normal, we can look on the pressure. This is the pressure one. Also, again, we have here the dimension, which is defined to the equation, and this is the value, which is 100,000, and it's uniform one. This is also about the detail of the problem. Then this is the structure. One of the main dictionary we can look on it is the system. On the system, we have these directory, which is for decomposition of the parallel, which is used by the FPI. Let's look at it. Here we can see there are different methods. We have simple, also we have hierarchical one. There is a manual, there is a sport also. And here there are coefficients when we are choosing the method. For example, here the method simple, and here we can specify these method how it's working. Indeed, this number will decompose this domain to number of the subdomain. Here, the subdomain will be decomposed to four smaller subdomain. Then we need to set up the coefficient here. So this is indeed in the x direction, this is in the y direction. And we will see the difference between them in the example. We will present it in the second part of this lecture. This is the structure of the case, how we run it. We can have a look on the how it's working also on the HPC cluster. At the University of Iceland, we have the module for OpenFoam. So on the area also we can run the OpenFoam simulation. There are different methods. Of course, when you work with the large data, it's perfect to use the batch method, and we will present it in the second one. However, because the module can be loaded on the system, we can work directly with command also on the area, and we will see how it's working. For example, we can look on the directories that we had it on our own computer, and now we can look on the HPC cluster where your save the data on the memory of the cluster. Here, let's look on it. For example, I have this folder for the HPC cores. As you can see, same, we have this depth chart 3D simple. Let's go to the there. So in the same uh, visualization we can see here, We have the zero directories, we have the constant directory, and we have the system one. For example, the constant, we didn't look on it in the previous section. If we go to the constant, here's about the constant values of the problem. You see here we have the properties of the problem, the thermal properties of the air, of the water, and the turbulence properties if we have, also about the G. So here we can see how we set up the information about the problem. For example, is the G, the value of the G here is the problem, as we expected in the y direction is the minus, and this is about this function about the equation. So in the same approach, we can work on this data on the physical asset, and we can run it. In the second part, we will have example how we can run this data, and we see how it works. Uh, so you saw how we run it on the personal system. We can work on it, and also about the cluster. And you see here in this user guide of the OpenFoam also, which has a different version. It's dependent that you are working in which version. We can use its guide, and it's has a good detail about the setup of each dictionary on the page, and also you can see about the post-processing how you can use the Power View interface and visualize the problem. In the example, you will see this Power View and how it's working, and we will run one simulation, and we will see its result. And we will try to see about to have a loop on the computing when we run it on the own system and when we run it on the HPC cluster. So I'm finishing the uh, first part of this lecture here. Also, I suggest you watch this video of the Magnus effect, which is the interesting phenomenon in the fluid dynamics. You can find the link of the YouTube for this video on the reference of the lecture. And we will continue in the second part of the lecture for the practical exam. Thank you.